Can you see the slides?
Yeah.
Great.
Yes, we can see the slides.
Let's start now.
Yeah, please begin when you are ready.
Yeah. All right. So thank you very much for inviting me on this invited space titled Current Trends in EEG Signal Processing for Brain-Computer Interface Applications, Challenges and Opportunities. I'm Mohammad Kafiul from Independent University of Bangladesh. So I'll just keep this outline to save some time, and let's go back to this motivation part. So what's the motivation? Basically, non-invasive brain-computer interface or EEG-based BCI. So BCI is nothing but a direct link between the human brain and an external computerized device, bypassing the injured or the normal pathway, diseased pathway. So it is motivated from the fact that if the person cannot use the motor function in a typical way, so because of some injury or any accident or any neurological disorder, so we are going to use some bypass path. We are going to record the signals from the brain, pre-process the signal, extract some features, and eventually control some of the computerized device to control them. So it can be a computer itself, can be a wheelchair, can be prosthetic arm or any home appliances or any computerized device. So the purpose of BCI is actually to either restore, replace, enhance, supplement, or improve the motor functions. And this is more or less mind-controlled devices, right? So this particular talk will be focusing on the pre-processing part of the EEG signal. And the idea is that because the EEG signal is often contaminated with different types of noise known as artifacts, and these presence of artifacts will eventually make some mistakes in the control of your BCI devices. So it is important that you detect and remove these artifacts reliably from the signals, and then the pre-process the signal and see that what is the output of this result of removal of artifact removal from EEG signal, how that does it affect on your BCI performance. So this is the basics of EEG and its characteristics. So EEG is nothing but electroencephalogram, which is a recording of the brain's spontaneous electrical activity in a period of time by placing electrodes on top of your scalp, just like this. So it consists of EEG rhythms and transients. So EEG rhythms are nothing but some non-overlapping frequency band in the low frequency regions, mainly known as delta, theta, alpha, beta, gamma. So more or less, this is in the frequency range from 0 to 100 hertz. And the amplitude range is very small in the microvolt range to some few millivolt. And the reason why EEG is very preferred over any other brain recording technique is that it is non-invasive. This is the most important part, and it is usually low cost compared to MRI machine. It is easy to use, easy to handle, and it has relatively fine temporal resolution. So moving on, if you take a look at the artifact characteristics and the sources, we can have artifacts from 3 different sources, such as environmental, experimental, or physiological sources. Now, artifacts can appear in a different form. It can appear locally, globally. It can have an irregular pattern or periodic pattern. So whatever it is, artifacts are actually some unwanted signal that come from non-neural sources. So it is important that you reliably detect and remove this artifact before the processing of your EEG signals or classification of EEG signals for BCI applications and for any other application basically. So the challenges with EEG signal is that it has not only very low amplitude, but whereas the artifact has very high amplitude, so often you have a negative SNR of your signal. Moving on, that's feeds somehow. Yeah. So moving on, if you take a look at the existing signal processing techniques for handling artifacts, we have a BSS, blind source separation techniques such as independent component analysis, ICA, canonical correlation analysis, CCA, and so on. So this kind of BSS algorithm, they work on multi-channel data and they're often offline. We have adaptive filtering, which requires an extra reference channel to work properly. We have wavelet denoising, which in wavelet denoising the choice of threshold is a concern. We have empirical mode decomposition, which is kind of an empirical method, and it is very computationally expensive, and it has storage problems as well. And then people have thought of some combining two different methods to make a hybrid one, such as Wavelet enhanced ICA or EMD enhanced ICA, something like this. So these kind of hybrid methods, they take the advantage of both the methods and complement the weakness of each method. However, as this hybrid two methods together, so obviously the computational complexity will be higher. And for BCI application, which requires real-time processing, so computational complexity is a big concern here. So therefore, we'll just move to the proposed algorithm later on. So this is just an typical adaptive filtering algorithm and example where how can you use this adaptive filtering algorithm to remove a certain type of artifact. So for example, you have a extra reference channel to record the ECG signal or iBlink or EOG signal, and then you can actually use adaptive filter to adaptively update your filter weight, and then use some RLS or LMS algorithm to eventually get the filter output, the clean EEG signal. So this is an artifactual EEG contaminated with cardiac artifact. This is the cardiac signal itself, and then you have the output of this adaptive filter is EEG signals from the ECG artifacts from the EEG signals have been removed. Moving on, this is an independent component analysis technique where you can remove some of the global artifacts that appear in all the channels, right? So here is the multi-channel recording, but you can see there are some muscle artifact as well as some eye blink artifacts. You unmix the signal by applying ICA, decomposing the signals into different independent components, and then you basically identify those in component that are corrupted with artifacts. So for example, the first component here is corrupted with a blink artifact. The last independent component is corrupted with muscle artifact. So you remove these two and then again apply inverse ICA to get back to the EEG's multi-channel domain again. So here your artifacts are removed. So ICA, they only work on a multi-channel process. So this is a wavelet transform. So wavelet transform is a nice trade-off in terms of it gives you both time and frequency resolution. So if you have a time series, you have only time resolution. If you have a frequency Fourier transform domain, if you apply FFT, you get only the frequency resolution. If you apply short time Fourier transform, you have both time and frequency resolution at the same time. However, the frequency resolution are uniform. But for our signal like EEG, which actually concentrate more on the low frequency region, so we need high frequency resolution in low frequency region and vice versa. Wavelet transform exactly provide this kind of resolution. It provides you better frequency resolution in the low frequency region and relatively lower frequency resolution in high frequency components. So this is something that can be used. So what the transform does, it actually gives you decomposed signals in different frequency, non-overlapping frequency bands, similar to the EEG rhythms, right? So this is the typical process flow of wavelet denoising. Apply wavelet transform, you have this approximate and detailed coefficient. You apply thresholding to selected wavelet coefficient, and then again apply inverse wavelet transform to get the artifact-free EEG. This is the empirical mode decomposition technique, which actually relies on decomposing the signal on different IMFs, or so-called intrinsic mode functions. So you can see that this is an EEG signal corrupted with iBlink artifact, and after decomposing into different IMFs, IMF4 has been found, IMF4 and IMF5 has been found that they are actually corrupted with this iBlink. So you can remove these two components and then get back to apply inverse EMD or inverse transformation to get the artifact-free EEG. Similarly, these are some of the examples of hybrid BSS method or hybrid methods based on blind source separation. The first one, it is the wavelet enhanced IC or wavelet enhanced BSS. this one is your EMDIC or EMDCCA. This one is the BSS along with SPM. So this particular SPM classifier is applied to actually classify between clean signal, clean EEG, and artifactual EEG. And even if you can apply some kind of regression technique, regression BSS to get clean signal. Now, obviously, in order to convert your brain signal into some command to control devices, you need classification. So machine learning classifications are there. We have supervised classification, unsupervised classification. If you are using traditional machine learning, then you have to do all this pre-processing and feature extraction. And then if you applying deep learning models, you basically feed the raw data directly without applying pre-processing and feature extraction. However, this is the latest tradition, latest trend applying application of CNN, and requires more studies to actually make this model robust. So if you think about the different BCI type and characteristics based on different perspective, we have different brain recording techniques such as invasive or non-invasive BCI, right? And the focus of this particular talk is obviously the scalp EEG, which is the non-invasive BCI. You can have BCI based on different EEG signal type, whether you give any stimulation or not. So if you have any visual stimulation or auditory stimulation, then you get evoked potentials such as P300, SSVEP, or SSAEP BCI. There is no stimulation, that means the EEG signal is spontaneous. So we can use motor imagery based BCI application. BCI can be of two types based on the mode of operation, synchronous or asynchronous. If the user needs to perform the mental task in a particular time window with respect to a queue, it is a synchronous BCI. Otherwise, if the user is free to perform at any time, it is actually asynchronous BCI. So now we are going to propose some artifact detection algorithm based on given all these existing technique. So what we are going to say that for artifact detection or to identify whether there is a presence of artifact or not in a particular EEG small segment known as epoch. Okay, so we are going to use 4 statistical parameters, and we're going to say that this is the probability of the presence of artifact in a particular epoch. Instead, we're not going to saying that whether we have artifact or not. It's not a binary classification. We're saying that okay, this is the probability of having artifact. And we are going to use these 4 statistical parameters like entropy, kurtosis, skewness, and periodic wavefront index. And then we propose one formula to actually calculate the probability. So the motivation is that entropy is the measure of randomness. We have found from the analyzing artifact and EEG characteristics, we have found that artifacts are usually more random than the EEG background segments. Artifacts have usually higher amplitudes of peaks than the which actually can be measured by kurtosis. Skewness, artifact probability distribution are often skewed, often asymmetric, and often skewed, either left or right skewed. We have found that artifacts tend to be aperiodic, irregular. Most of them are irregular compared to the EEG signal itself. So therefore, first we have tried to identify the probability of having artifact, and then we say that it is up to the user and at what percentage, at what probability of artifact, the user will decide whether he or she will go for denoising of that artifact, removal of artifact, or keep the signal as it is. Okay. So this is the user-defined function, user-defined probability that can be set by the user, and then if the probability is more than the set user probability, then we can go for the denoising. And the denoising has been done in SWT, stationary wavelet transform domain. The reason we have chosen stationary wavelet transform and discrete wavelet transform or continuous wavelet transform is the fact is that it's a nice trade-off between this DWT and CWT in terms of complexity and accuracy. SWT is transformation invariant. And we have found that wavelet transform is more suitable because it is suitable for non-stationary, non-linear signal processing, and our EEG signal is exactly the same characteristics. So we have done, we have mapped our SWT coefficient, decomposed wavelet coefficient into different frequency band, obviously, and that we have tried to map with the different EEG rhythm with relevant BCI studies and the artifact type. So, for example, if you think about the P300 event-related potential-based BCI study, we have found that P300 is actually relevant with theta and delta rhythm, which is relevant to the approximate coefficient level 5, A5 and D5, detailed coefficient level 5 of your wavelet coefficient. And we have found that mostly movement, cardiac, and blink artifact, they're actually going to affect more on this particular frequency band. And similarly, motor imagery based BCRS, BP. So this is the, based on these statistics, based on these characteristics, we have carefully denoise our wavelet coefficient in order to remove artifact. So that we wanted to make sure that it is not our only job to remove as many as artifact possible, but also at the same time we want to see that the background information, original signal of interest information is preserved. Excuse me. So moving on, we have tested our algorithm both on the simulated dataset and real dataset. We have used BCI competition 4 dataset to see the after effect of artifact removal on the BCI classification. And also we have done some analysis on fully simulated data so that we can measure the amount of artifact, how much of amount of artifact removed, how much is the distortion bring to the signal. So this is the simulated experiment where this is the artifactual EEG sequence and the probability mapping of this artifactual EEG sequence has been provided. And then we've applied the algorithm to remove artifacts, and then we can see the probability of the artifacts in the reconstructed artifact-reduced EEG sequences is much more as expected. So we have actually also extracted 6 different artifact templates based on mimicking based on real artifacts, such as muscle artifact, eye blink artifact, EOG artifact, cable movement, electrode pop, and of the subject themselves.
Hello.
That the signal to noise and distortion ratio after removing artifacts. That's yes, Linda. Can you say something?
Sorry, just now
Can't
your
hear you, Linda.
internet connection is not very good, so can't hear what it's okay now. Please go on.
How long it is unstable? How long it is unstable? How long the internet connection is unstable?
Just a few seconds.
Just a few seconds. Okay. Can you hear
Yes,
me now?
please go on.
Properly?
Yes, you
Okay.
can go on now.
Okay. So let's resume. So this is the most important part that we'd like to show you, that the impact of artifact removal on the final BCI performance is that you have improved BCI performance, in terms of ROC curve after artifact is removed compared to the before artifact removal. So this is something that is more important to us, whether the impact of artifact removal is actually helping us or not in our BCI performance. That is something that is the most important part. So these are some of the quantitative evaluation, of our proposed method with respect to the other methods, existing methods. So these are, all of them are actually different performance metrics. The higher, the better. And we have seen that, and all the left bars are actually proposed one. So we have seen that in each cases, our proposed one performs better than the existing algorithms. And for the comparison, we have studied Wavelet enhanced ICA, Wavelet enhanced CCA, EMD, EMD ICA, and EMD CCA. And not only this performance, but what is most important for BCI application is the computational time, because BCI application requires real-time computation. So therefore, we have found that the proposed algorithm to process 1 second of EEG data, it requires 0.9 millisecond, whereas anything that is related with EMD, they require more than 90 milliseconds. So compared to 0.9 milliseconds. So you can easily see that 100 times higher for EMD-based algorithm. So this is something that is actually will help us in future research, that maybe this is more important for BCI application, that is the computational time. It has to be computationally inexpensive, your algorithm. So this is for those who want to start EEG-based BCI research. So they can easily use BCILAB, which is a MATLAB compatible toolbox, open source toolbox. It has a lot of features. If you do not want to, develop your own signal processing and machine learning algorithm, you can actually use the built-in functions from BCILAB. All the you can, starting from signal processing to classification, you can find all the types of the algorithm, and there are at least 100 advanced plugin or extensions available for BCILAB. So in conclusion, if you see the challenges, that the first challenge is actually the computational complexity, right? It has to be low computational complexity so that it can be implemented on real time. And sometimes in order to have this portability, it has to maybe applied on chip, on the fly decision making required. Therefore, computation complexity is a major task. And the current system that are available, they are very expensive, so they are not affordable. So obviously, the disease, disability, or accident do not come only for the rich people. So everyone should be able to afford this kind of system. So this is a trade-off. Always the challenge is the trade-off is between the BCI performance and the complexity, cost, and visibility of the BCI system. And the robustness of the signal processing classification algorithm is also a challenge, because sometimes it works for a particular data set, sometimes they do not work for the other data set. That's still a challenge. So the recommendations are that you can actually build BCI application specific model, because what the artifacts that are responsible for MI may not be responsible for P300 based BCI. So it has to be an application specific model, or you can make an artifact specific model given that which artifact supposed to affect more of your BCI application. You need a standard performance evaluation of your BCI system, or also for your signal processing system, so that you can actually quantify your evaluation through some standard procedures, right? And the ground truth data is something is often not available, so this is also a challenge. Therefore, we should make more experiments to actually make available of this ground truth data, so that all of the researchers can actually use those ground truth data for as a gold standard to validate their performance of the BCI system. And these days, it's days of deep learning neural networks. So you're always welcome to actually try deep learning neural networks, because with deep learning you can actually avoid so-called traditional signal processing or feature extraction techniques. So in my opinion, the future opportunities is that the way that advances is being made in terms of the recording technology, in terms of the EEG headsets, from wired to wireless, few channel EEG recording headset, and the advancement in signal processing, and also the advancement into more robust machine learning or deep learning model architectures. Plus, if you train your BCI user properly, so user specific training and tuning, overall this kind of setup may lead to achieve a sustainable, feasible, and affordable BCI system for those people who are in need of it to improve their quality of life in the future. So with that, I'd like to end the talk here. So thank you very much once again for your patience, and I'm ready to questions session. Thank you.
Thank you very much for Islam's excellent speech. Now it is Q&A time. If you have a question for Islam, please click chat and enter one, or you can directly type your question in the chat box. Okay, any question from the audience? Well, if you have, maybe you are preparing for the question, if you have question for exam later, please type your question in the chat box, and Professor Islam will be glad to answer it in the chat box. Thank you again, Islam.
Thank you. Should I stop sharing?
Yes, yeah.